All right, this video is going to go through 18 through 20 in your work energy packet. So we're going to bring back some impulse and momentum and kind of recap on some work stuff. Okay, so it says in what time, so you're looking for time, and distance, so you're looking for distance as well. Can a 1,000-kilogram car, that'd be your mass, stop? There's your VF. If it's moving at 30 meters per second, there's your VI. And it has a 3,000 Newton braking force. This force is going to be negative 3,000 Newtons. So you got a lot going on there. Okay, so we're going to do time first. Okay, so this is where we bring back that kind of impulse momentum. Okay, so you can do force times time equals mass times change in velocity. Okay, because you have force, which would be negative 3,000. Time you don't know. Your mass is 1,000. VF minus VI, so 0 minus 30. And if we do our math correctly, we should get a stopping time of 10 seconds. Okay, so this is just bringing back some impulse momentum to kind of help us there. Okay, and then distance. So remember we talked about work equals force times distance. And that equals change in kinetic energy, so 1/2 mv final squared minus 1/2 mv initial squared. Okay, so my force would be negative 3,000. My distance, don't know. Okay, I'm coming to a stop. Okay, so this whole thing goes to 0. So 0 minus 1/2 your mass, which is 1,000, times your VI, which is 30, and that's squared. So we're going to get a distance of 150 meters. Okay, so it says in what time distance can the car in the previous question stop if it's moving at 60 meters per second? So this is kind of that relationship thing where, well, what happens if we double our velocity now? So we're going to figure out how much time it takes and what's going to happen to our distance if we double that velocity. So we're going to do the exact same steps. So negative 3,000 because your braking force didn't stop or didn't change. So times time equals mass, which is 1,000. Your final velocity is 0 minus, now your new initial velocity is 60. So you're going to get a time of 20 seconds. Okay, so that was a direct relationship. So that meant if we doubled our velocity, our time doubled as well. Now let's look at our distance. Okay, so force times distance, so negative 3,000. Distance equals, still coming to a stop, so 0 minus our initial kinetic energy, 1/2. Our mass is 1,000, and now our new velocity is 60. Okay, so if we do our math correctly, we're going to get out to 600 meters. Okay, so this is that relationship we kind of talked about, is since velocity is squared, it's going to raise everything else exponentially. Okay, so if you double the velocity, it actually quadruples the distance. Okay, so this is just mathematically showing you how that relationship happens. Now, moving on to this assignment part. So what we're going to do is we're going to talk about define work in terms of physics and its mathematical representation. Okay, so one thing is that work should require a change in energy. Okay, so it should produce a change in energy. I'm not going to really worry about writing out the sentence. You can if you want to. Okay, so which can be change in kinetic energy as well. Okay, so point here is that work requires energy. Now, work is also done by applying a force over a distance. So work equals force times distance. So our force has to be applied in the same direction as our distance. So remember, just watch out for things like this. If your force and your distance are perpendicular, this would be a no work scenario. So what are the units for work? Okay, so we talked about joules. Okay, so characterized by the letter J, or force times distance, that would be newtons times meters. So either one is acceptable, whichever one you prefer. Number 2, if a physics student pushes a box at a constant velocity with a force of 25 newtons over a distance of 10 meters, what amount of work was done by the student? So I was given a force, I was given a distance. So this is just a basic work equals force times distance. Okay, so don't make every problem as complicated as it needs to be. Okay, this is like, since I gave you force and gave you distance, you don't need to start looking for other things. Okay, so try to take simple problems as they are and don't overcomplicate them. So work equals force times distance, so 25 times our distance, which is 10. And we get a value of 250 joules. Now, if the student pushes down the same box at an angle of 30 degrees above the horizontal with a force of 28.9 newtons and moves the box the same 10 meters, what is the work done by the student? So now I'm pushing down at an angle, and the box is going this way. Okay, so I need to figure out how much of this force is actually happening in the same direction as the box. Okay, so this 28.9 is not the exact same direction as my box. So I got to find that side of the triangle, and we know our angle is 30. So this is where you get to use your cosine thing. Now you can do this all in one step if you want to. So remember, so work equals force times cosine of theta times distance, or you can break it into pieces. Okay, so if you want to find that force, okay, so if you want to find that Fx, you would just do your force times cosine of theta. So it'd be 28.9 times cosine of 30. Okay, so either way works, and you get a value of 25.03 newtons. That's how much of that force is going in the same direction as the box. Okay, then you can plug it into your work equals force times distance. Okay, so you can do work equals 25.03 times your distance, which is 10, and you get 250.3 joules. Now, some people like to do it in steps like that. If you want to do it all in one swoop, like this equation right here, by all means, go for it. We give you that equation, so whatever works for you. So what is kinetic energy? Okay, so kinetic energy, oops, let me fix that. So kinetic energy equals 1/2 mv squared. Okay, but it's also due to movement. Okay, so it is due to objects' motion. Okay, so that's the literal term for it. And what is the equation for it? We just wrote it down right here, so I don't have to worry about writing that again. Okay, so that is your equation. Now this problem right here, this is basically just rewriting equations. I'm not going to get too hung up on 6, and we're going to go ahead and mark this off. I'm not going to worry about this part. So if I want to find acceleration due to Newton's second law, so remember we said Newton's second law is force equals mass times acceleration. So A would technically be F divided by M. Okay, so your initial kinetic energy would be 1/2 mv initial squared, and your final kinetic energy would be 1/2 mv final squared. And your total change in kinetic energy, so remember this little triangle right here means change, would be 1/2 mv final squared minus 1/2 mv initial squared. Okay, so this is kind of just a recap and formulas there, not going to get too hung up on that. 7 from above, what is the relationship between work and kinetic energy? So remember, work equals a change in energy. Okay, so that is a relationship, they're directly related. Okay, so you would do 1/2 mv final squared minus 1/2 mv initial squared. Okay, so that's your equation there. Now in terms of physics, define energy. Okay, so energy is a quantity that can be used to perform work on an object. So that's the definition of energy there. So let's try to solve some. So what, it has more kinetic energy, a car at 30 meters per second or a bus at 30 meters per second? So we know 1/2 mv squared is our equation for kinetic energy. Okay, so in this case, they both have the same velocity, so that means mass is going to be a factor. Okay, so the bus is going to have higher kinetic energy. I don't know why I put 2 S's on that bus. Not thinking straight today. Okay, so the bus, because it has higher kinetic energy, because it has higher mass. Okay, number 2, a bus at 30 meters per second or a bus at 50 meters per second. Okay, which one's going to have most? Okay, because of this right here. Okay, our masses are the same, but now our velocities are different. Okay, so higher the velocity, higher the kinetic energy. All right, now we're looking for the kinetic energy of a car which has mass of 1,000 kilograms. Okay, a 1,000 kilogram car is traveling at 20 meters per second. What's the kinetic energy? So KE equals 1/2. My mass is 1,000. My velocity is 20, and that is squared. Okay, and that's going to come out to, let me fix it real quick. That's going to come out to be 200,000 joules. If the braking force of the car is 40,000 newtons, how many meters does it take for the car to stop? Okay, so remember we talked about force times distance equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, I already know my braking force, that's negative 40,000. Times distance, we don't know. Now we're coming to a stop, so that means my final kinetic energy would be 0. So 0 minus 1/2. Well, we already know, I don't even have to solve that part. We already know our initial kinetic energy was 200,000 joules. We're going to save ourselves some time. So solve for distance, and you get a stopping distance of 5 meters. Now, if the same car is now traveling 40 meters per second, what's our new kinetic energy? Okay, so KE equals 1/2. My mass is still 1,000. My new velocity is 40, and that's squared. And I get 800,000 joules. So this is what I'm talking about, is when you double that velocity, it actually quadruples your kinetic energy. Number 6, what is the stopping distance required to stop the car from 40 meters per second? Okay, so we can do the same thing. So braking force is still the same, negative 40,000. Your distance, we don't know. And you're coming to a stop, 0 minus 800,000. And you're going to get a distance of 20 meters. Okay, so it quadrupled that stopping distance. So this is kind of just a recap, just to show you what's happening. So at 20 meters per second, we had 200,000 joules, and it took us 5 meters to stop. At 40 meters per second, we actually quadrupled our kinetic energy to 800,000 joules, and our stopping distance is now 20 meters, so that quadrupled as well. So when speed doubles, kinetic energy actually increases by 4, so it quadruples. When speed doubles, so same concept, the stopping distance also quadrupled by 4. Now, what type of proportion exists between speed and kinetic energy? So that means kinetic energy is directly related to velocity squared. Okay, so just make sure you're careful with that, is once you double velocity, it quadruples. Okay, the kinetic energy, or if you triple velocity, it's going to go up by 9. Okay, so just pay attention to that squared right there. It is direct because when one goes up, the other one goes up. But since that squared is there, it's going to affect how much it goes up by. Now, what type of relationship exists between speed and distance? It was the same. Okay, distance is directly related to velocity squared as well. So that means in this last example, when we doubled our velocity, it quadrupled our distance. Okay, so again, just watch out for that squared there. And that will end that one.